Welcome to the GT350 Garage. My name is Walter, and in this video we are going to be talking about high compression from a tuning standpoint and high compression from an application standpoint, and the association of high compression with combustion efficiency, because we need combustion efficiency out of the engine to be able to properly utilize that high compression that we're going to build into the engine. This video is going to kind of bridge my engine build with some of my tuning content videos that I've posted in the past, and hopefully this explanation will give you some food for thought and get you on task to change the way you're thinking about how you're going to build a high compression engine, because there's some do's and some don'ts, and there's some things that cause problems when you're trying to run high compression that are easily avoidable. Let's get into kind of the meat and potatoes of this. If you're new to the channel, subscribe. There's going to be more stuff like this. If you like the video, definitely give it a thumbs up. I appreciate that. It helps the algorithm and more people get to see it. But anyways, besides that, let's talk about this. So how did we get to where we are in the industry right now? And where we're at in the industry is we still have this crowd of individuals, mostly my generation and older, who are under this misconception that you have to have high octane fuel to run high compression. And this is the thing I want to make very clear initially. High octane fuel is a band-aid for poor combustion efficiency. Okay? And people are going to argue, no, it's detonation and this and that. And we're going to get to this, and it's going to make a lot of sense really quick. So, high compression in the 60s meant shoving a giant dome into a giant combustion chamber and using the dome on the piston to take up the space in the combustion chamber so that the final compression ratio was higher. Case in point, L88 427 Corvette. They're like 110 cc heads. Well, 110 cc head on a 427, that's huge, okay? That's massive. All right. 427, 7 liters. 7 liters divided by 8 cylinders. So half is 3.5. So each cylinder is roughly 0.875 or 875 cc's, right? So you're stuffing 875 cc's into a combustion space that, with the distance above the top ring, the distance between the top of the piston to the deck, thickness of the head gasket, all in, your total combustion volume is like 125 cc's, maybe a little bit more, but at 125 cc's, if you're stuffing 875 cc's into that, your compression ratio is like 9-to-1. Okay? You check my math. I think I'm pretty close. Your compression ratio would be like 9-to-1. Well, how do we make a 9-to-1 compression, 12.5-to-1 compression? Put a dome on it! Okay? The problem is we're putting a dome on it that's the size of Mount Everest. And putting that giant dome on the piston means it's going to be in the way of the flame travel from the spark plug to the rest of the combustion chamber. So essentially, if we've got our spark plug on one side of the combustion chamber, the flame has to travel around and over the dome to get to the rest of the cylinder. Why aren't we making the combustion chamber and the cylinder head smaller, leaving a nice flat top on the piston, and then just having the combustion process spread out in the smallest area possible? Oh, hey, that would require designing a new cylinder head, and the engineers didn't want to do that. So making pistons was cheaper than designing and casting a new cylinder head. Hemis are the same thing, and to the point that Hemis quite often have 2 spark plugs. You look at all the Gen 3 stuff, 2 spark plugs per cylinder. Why 2 spark plugs on a Hemi? Well, if you can start the fire at exactly the same time in 2 places, it's going to burn at the same rate, it's going to meet in the middle. You won't have a detonation event, but you will cause the combustion to happen faster, and that's the only way they're getting combustion efficiency out of those Gen 3 Hemis, is they're running 2 spark plugs on them. Okay? This is why Ford went to a dual overhead cam V8 in the Mustang Cobra in 1996. You put the spark plug in the middle, the distance from the spark plug to the cylinder wall is shorter, but it's also the same in every direction, which means you don't have the inefficiencies. They also ran a flat top piston, which meant that from the spark plug to the top of the piston, the combustion took less time. So you weren't wasting time with a long distance from the spark plug to the farthest reaches of the combustion chamber. You essentially made the combustion chamber faster. Okay? So when you talk about a fast combustion chamber versus a slow combustion chamber, a 427 L88 is a slow combustion chamber. A Hemi is a slow combustion chamber. Most of your wedge type cylinder heads are slow combustion chambers. But we can fix that. We can change that. And depending on the cylinder head that you're running and depending on the way you're building your engine, you can absolutely change that. So let's take a look at the engine for my Shelby now. And I want to show you the cylinder head and the piston. And you're going to get to see exactly what's going on. Okay, let's talk about what we're looking at here. This is the short block for my Shelby. This is a 2cc dome. So it is going to take up 2 cc's of space in the combustion chamber. This piston is at 0 deck. We have our valve reliefs, and our valve reliefs, normally 2 reliefs this size would net us 4 to 6 cc's of positive volume. That would increase the size. But because of the size of this dome, the net gain is negative 2 cc's in terms of building compression. So we can subtract 2 cc's from our total combustion volume when the piston's at top dead center. That's one of the tools that I used to raise the compression on this engine. This head gasket is not the head gasket I'm going to run, and I'm using it to show you guys that there's a lip here at the bottom and at the top. And this lip, because this gasket is a 4100 bore, the bore of the cylinder is a 4030. There's a 35 thousandths difference between the cylinder wall and the gasket. That creates a dead space all the way around the gasket. And especially over here along the exhaust side, and especially up here on the top opposite of our spark plug, if we're going to have a failure, it's going to be because of the gasket not clamping or because of mixture problems in these weak areas of combustion efficiency where it'll actually cause the gasket to fail. And basically it beats the gasket up because you have a combustion event creating pressure between the block and the face of the head. We don't want that. So the gasket I'm going to run is a Cometic 4030 bore to match the block, and then I'm going to run a 40 thousandths thick. Now, the 40 thousandths thick, because this piston is 0 deck on the quench pads, 40 thousandths thick gives me 40 thousandths from the face of the head to the quench pads. What's going to happen is I'm going to squeeze any mixture that's down here. I'm going to squeeze that mixture out towards the dome, and the dome is going to push it up into the combustion chamber towards the valves. On this side, I'm going to squeeze any mixture I have out here in towards the valves, and that's going to create turbulence, and you're actually going to end up with tumble occurring in the chamber, mixing the air-fuel mixture after combustion has started, which increases the speed that the combustion travels through the mixture and decreases the amount of time it takes to reach peak cylinder pressure. I hope you guys understand where this is going, because that means we need less ignition timing. We do not need 36 degrees of time from the piston coming up the bore, 36 degrees of time to get to top dead center to have peak combustion occur with the piston 15 to 20 degrees down. Instead, we're going to need about, with this compression ratio, we're going to need about 26 degrees to 28 degrees. And that's going to be dependent upon what I find with this particular engine once it's in, with this particular camshaft, with this particular cylinder head. Every engine is different. Trying to throw a magical number at every engine doesn't work. You cannot go off of every engine is going to be the same. You have to treat them all as individuals. Now, this particular combustion chamber, you can see how small it is. This head's been milled 66 thousandths again, and that reduced the chamber size from 56 cc's to 46 cc's. I want to give you an idea of how big a 60 cc chamber is. Let's see. This is a Twisted Wedge 170. These were originally going to be the heads that were going to go on the car, and I decided to put this project off and go with an off-the-shelf head. These will get finished at some point, and I will use them on something. But this particular cylinder head, you can see how deep the combustion chamber is relative to this chamber is the width of my index finger. This chamber is wider than my index finger by almost 1/4 of an inch. So it's a pretty substantial difference for two reasons. One, the Twisted Wedge 170 is a 15-degree valve, which means that the valve has more angle, which raises this edge of the valve in the chamber and lowers this edge into the piston more. So these produce more piston to valve clearance than the 15-degree head. But also just simply because of the depth of the chamber. So there are very, very specific reasons that I do the things I do when I'm building an engine. And I'm hoping that by showing you guys this example and showing you exactly what I'm doing on my engine, you can see logically how the system's going to work. Let's take the gasket and just overlay it on the head here really quick. So everything inside this gasket is essentially your quench pad. So this whole area in here, anywhere the piston comes up to this is available quench pad. We want to make sure that the piston is as close to this shape as possible so that we get the maximum quench action in the chamber to create the turbulence that is in turn going to produce a more well and thoroughly mixed combustion mixture. Okay, so now you have an idea of what's going on in my build. And let's talk about that from this drawing, because this drawing is kind of representative of what I just showed you. So we have this more compact combustion chamber. The combustion chamber is a little bit deeper, but it's more compact. And we have these quench pads on both sides, so it makes the combustion chamber effectively smaller. Okay? The other thing is, when we look at the way it interfaces between the piston and the cylinder head, we have our quench clearance between the piston and the deck. That quench is going to squish the air-fuel charge out. It's going to go past the dome. It's going to hit the edge of the dome, and it's going to shoot up into the upper portion of the combustion chamber, and it's going to start moving the mixture along the combustion chamber that way. Okay? And then you're going to have quench on this side, and it's going to be shooting the air-fuel mixture across the bottom of the chamber. It's going to hit the valve reliefs, believe it or not, and it's going to cause the air-fuel charge to turn this way, and it's going to cause a tumble effect in the combustion chamber. That speeds up the rate that the air-fuel charge is moving in the combustion chamber, and it actually creates a very similar effect to the tumble that you get on a 4-valve per cylinder engine. I know a lot of guys don't like hearing this, but there's a lot to be learned from small engines. There's a lot to be learned from the sport compact market. There's a lot of information out there that, yeah, you might be a V8 guy, but knowledge is power, okay? And this is literally knowledge that I use to make more power. So what we're accomplishing is two things. One, the cylinder head is going to produce swirl as the intake valve opens and the piston's moving down. So we're already getting some homogeneous mixture as a result of that swirl. Now we have a swirl effect, but we also have the quench effect, and we end up with tumble during the final few degrees of piston travel, and during the time and period where we've started the mixture burning. So as we if we think about this, the piston is still coming up, and if we're igniting this with the piston 30 thousandths, 40 thousandths, 50 thousandths down the hole, and it's squeezing this mixture up into what we've just ignited, it's going to help carry that ignition. It's going to help carry that ignited mixture through the chamber, and it's going to help mix the mixture simultaneously to the start of combustion, which makes for a more efficient process. So this is how I'm getting away with running over 12-to-1 compression in my 289. And this engine's designed to run on 91 octane fuel. Could it benefit from more octane? Yeah, maybe a little bit. I mean, if I wanted to put some 96 to 100 octane using the same octane rating, AKI, not RON, because that throws everything off. If I go from 91 octane AKI, R plus M divided by 2, to 96 to 100 R plus M divided by 2, if I'm using octane on the same scale, will the engine perform a little bit better with a little bit more octane? Yeah, maybe. I might be able to squeeze a little more power out of it. Is it going to be necessary? Probably not. And that's kind of the exciting thing about the way this engine's being built. A lot of you guys want performance, but you go about things the wrong way. And there needs to be an understanding of some do's and don'ts. So right now I'm going to give you the do's and don'ts. Do run high compression. If you're running naturally aspirated, I wouldn't personally build anything today less than 11-to-1 compression for a performance street application. And that's me personally. I would run 11-to-1 compression minimum. 12-to-1 to 12.5-to-1 is actually still very doable if you're playing with the right parts. So that's the start of this. Make sure that the piston shape matches the combustion chamber shape. You want the flattest piston possible. So in order to have the flattest piston possible, you need to have the smallest combustion chamber possible. And this is where a lot of you guys get into you get into trouble. You think, well, I've got these 66cc heads or these 72cc heads. I'll just buy a dome piston and put a dome in it. Well, now you're back to 1965 and you're killing your combustion efficiency. It's just not going to work as well. Stop using giant combustion chambers if you can help it. Okay? Um, if a cylinder head is offered with 2 combustion chamber sizes, order the smaller combustion chamber size. The heads I just showed you, they were 56 cc's out of the box. I had them milled 66 thousandths. They are now 46 cc's. Okay? That's a tiny combustion chamber. But that's how I'm making this work. The smaller combustion chamber means I don't have to have a crazy dome. So I do have a dome, but it's a very small dome. Okay, this is how we have to approach these things. We've got to be looking at the big picture. Okay, let's say you're building a big displacement engine and you have a smaller combustion chamber head. Do not buy a generic dished piston. What do I mean by a generic dished piston? If the dish in your piston is round, it's generic. If the dish in your piston is football shaped, essentially, if it's in the center and you've got a quench pad on each side, and you've got this giant dish in the center that's kind of D-shaped on both ends, it's generic. Don't expect a generic piston dish to perform well in your engine. There's a piston design called an inverted dome. And an inverted dome is a type of dish where the dish matches the shape of the combustion chamber. If you have to run a dish, you need to run an inverted dome. Spend the money, do it right, you will thank me, because an inverted dome is a much more efficient design, because now all we've done is we've taken our combustion chamber shape and we've extended it down to create a lower floor, but we retain our quench pads. And by retaining our quench pads, when the piston comes up to top dead center, we still get that quench action, activating the charge in the middle of the chamber. So there's all kinds of benefits to an inverted dome where there is zero benefit to a generic dish. So you have to be careful about your piston selection. You have to be careful about your cylinder head selection. Don't buy a giant chamber size head and expect it to perform well. Not every chamber shape works well. Okay, case in point, if I was building a Cleveland, I will use a closed chambered head. I will not use an open chamber Cleveland head. Why? Because they're horribly inefficient. A closed chamber Cleveland head can be maximized for performance, and you can make a lot of power with that chamber. You can't make any power in an open chamber head because you have all this dead space out over the top edges of the piston, where you actually end up with detonation and pre-ignition sources. It creates a horrible inefficiency in the combustion process that makes it so that the engine just simply doesn't want to run well no matter what you do. And I'm gonna have comments on this one. I know there's gonna be somebody out there that's gonna tell me I'm wrong, that their dome piston is more efficient and they're running 36 degrees of timing, and they can run 36 degrees of timing and make more power because they're running that timing. And that's a key point to this inefficiency. When you're running the overhead valve, or the 4-valve setup, this engine at 11-to-1, or this chamber shape at 11-to-1 compression with a flat piston, it's going to want like 27 degrees of timing. My engine at a little over 12-to-1 compression is going to want 26, 27 degrees of timing. Okay? That's what it's going to want. And it's going to want that not because it's too much compression. That's what it's going to want because that's how long it's going to take for peak cylinder pressure to build at approximately 15 degrees after top dead center. So because I have a faster combustion chamber, I don't need as much ignition timing. If I put a giant dome in a big empty chamber, I'm going to have to run more timing, and I'm going to need more octane. And the reason I need more octane is I'm going to have hot spots in the off places in the chamber, and they're going to want to ignite the fuel. And as the pressure builds in other places in the chamber, it's going to also aggravate that fuel out in the far reaches and cause it to want to combust from the pressure. So it's a very complicated process. Hopefully you understand where I'm going with this, and you can see why I'm building my engine the way I'm building it. And hopefully this gives you some food for thought for your next engine build, and maybe even your current engine build if you're having problems, why you might be experiencing problems. And I'm going to be doing some more tuning content soon. I hope that this leads to some good discussion and not just a bunch of, hey, you're wrong, you don't know what the hell you're talking about. I really do hope that this leads to some good discussion. So with that, I thank you for watching, and I'll see you soon.